solution to an infinite series of the binomial theorem of Math 143 or 147 or algebra in high school. The binomial theorems, you remember, if your exponent is a positive whole number, like 2 or 3 or something, there's the formula for a plus b quantity squared. And you get a squared plus 2ab plus b squared. And in general then, if you have your first term as a 1, and this is some other number, 1 plus x to the n, if the n is 1, 2, 3, so on. That's the binomial theorem, say, in high school or Math 143. This extends for the possibility that n is no longer a positive whole number, but, for example, is the half power or is a negative integer, something like that. And then what you get is an infinite series, because if the n is not a positive whole number, as we'll see, the terms just keep on going. Nevertheless, this series, which we call the binomial series, is something that people use in other classes, and I end up over there with what we want are the powers. We want a series for this in powers of x, which will just be a polynomial if the n is a positive whole number. So if you set out to make the Maclaurin series for this function, you notice that you can certainly do the derivatives whether the n is a positive whole number or not. Also notice that f of 0, thinking of a Maclaurin series where you get your coefficients by taking f of 0, f prime of 0, f double prime of 0, and so on, that your f of 0 would be 1 plus 0 to whatever, raised to whatever power this is, whether it's a whole number or not. 1 to some power is still 1. So that's going to be a 1. In the same way, f prime, then, whether the n is a positive whole number or not, you'd bring the n down in front, and the new exponent is the old one minus 1, and then you times, according to the chain rule, by the derivative of what's inside parentheses, which is a 1. So f prime of 0, then, is n times 1 plus 0 raised to this power, and again, 1 to any power is 1. The subtracting 1 each time, if it's a positive whole number, you'll count down to 1, and then the next time out it would be 0. And so you get a polynomial. But if the n is not a positive whole number, this doesn't stop. For example, if the n is the half power, then this is 1/2, and then this is minus half. And then next time you'd have a half, and then minus a half, and then this would be minus 3/2, and so on. So it keeps on going, and you get the infinite series. So you can see there's the pattern to this, using your rules for derivatives. Your third derivative, evaluated at 0, would be this product, and your kth order derivative, which you see will be n minus 1 on down to n minus k plus 1. Notice here, for example, if this is 3, if k is 3, you have n minus 1, n minus 2, which is n minus 3 plus 1. So this is your general pattern here. And then your binomial expression, if you're evaluating this thing at 0, again, you have the power of 1 here, so you just have this product of the factors. And so notice that for this to work well, it has to be in the form 1 plus x, because otherwise you can't simply say when you're evaluating these derivatives at 0 that you just have some power of 1 and that's automatically 1. So it's important that you work with a binomial series in the form 1 plus in order to be able to say all these statements. F prime of 0, F double prime, F triple prime at 0 will just be the product of the n minus 1, n minus 2, and so on. So we have our general formula here, and if you call the k, which is the order of the derivative, the index, as we do in a week from today, we'll talk about computing pi, different ways people have done it historically. You'll find there's more to it than you might think. And then a week from tomorrow, you can either come and take the final and be done with it if you like, and if you don't like, you can stay away and come the next week and take it. Oh, and one last thing then is that the fifth, let's see, no, not the fifth, the 29th is the last day for homework. So, end of next week. You don't plan to come on the 29th, then it would be the 28th, obviously. And I'm hoping to get them either today or tomorrow from you. And everybody should have a copy of the take-home part of the final. And okay. Uses, and so naturally you wonder what it is if you are looking at Maple. So if you ask Maple for a Taylor series and give it a command like this, say you define a function as 1 over 1 plus x, which is the sum actually of a alternating geometric series, as we have seen, you might type something like this. Series, you can either type series or you can type Taylor, either way. Then the function, which if you've already defined it, you can say f of x, or if you haven't defined it, you could put the expression here, 1 over 1 plus x, and then comma, and then powers of x minus 0 is what you mean. In other words, just powers of x if you write x equals 0. If you wrote x equal 1/2, say, then it would come out in powers of x minus 1/2, and so on. And then you have a comma and then a number. So that number that the command requires does two things. It tells how many terms altogether are in the polynomial that you get, your Taylor polynomial. So the degree of the polynomial is this number minus 1 always. And you notice that because your constant is like starting with x equals 0, you get your 6 terms going through x fifth, and then this number appears as a power in this symbol, which is a large letter O, called big O, if you're saying it in words, of x to whatever number here is whatever number is there. So what I'm talking about first this morning is how you interpret this symbol, which relates to the error formula or the remainder formula. If you have a function that's not exactly a polynomial, then the Taylor series, or Maclaurin series in this case, gives you a polynomial and then a remainder, which is to represent the difference between what the polynomial would give you and what the true function value would be. The only time that this would not be present is if your function were a polynomial to start with. Then it would be, its own Taylor series would be a polynomial of that same degree, and then you wouldn't have any error. But for sine and cosine and so on, you do. When you say the polynomial value is the sine value or cosine value or log value, whatever it is. So the handout that you have, that's the copy of the book, which is in chapter 7, that defines the symbols little big O and little o. And as they would print, the difference would be in the size of the circle there. If you look at how they're printed in the book, you can see how big O looks and how little o looks in print. So, definition then, a function has order smaller, function f has order smaller than function g, or is of smaller order than g, or is of order smaller than g, any way you want to say it, as x becomes infinite when the limit of the quotient is 0. So if you can, for example, set it up as a L'Hopital rule limit as x goes to infinity of a function that you want to show is little o of another function g, has smaller order, you have that if your limit will be 0, which you might be able to get if your form is infinity over infinity, say, by doing successive derivatives or using some other limit theorem. So, for example, log x is little o of x because this limit, which you see is infinity over infinity, if you do the derivatives, is this limit from the log 1 over x, this limit's 1, and then your limit of 1 over x is 0, because 0 is a horizontal asymptote. Or you could say x squared is little o of x cubed plus 1. Notice this polynomial has higher degree than that. So again, the limit, if you set it up as a L'Hopital rule limit, you could either do a couple of derivatives and take the limit and get 0, or you could divide top and bottom by the highest power here, by x cubed, and see that your limit is 0 that way. If you divide it by x cubed, this would become 1 over x, and this would be 1 plus 1 over x cubed, and you get zeros. We also have big O symbols, which are the symbols that Maple uses. And so if you assume your functions f and g are positive for all x from some point on, and So the k then is could be any real number that's large enough so you could say these are positive once you're past that. Then you'd say f has at most the order of g, whereas here you're saying f has smaller order. Smaller order means the limit of the quotient will be 0. When you say at most g, then that does not require the limit to be 0, but simply that you can show that the quotient will stay bounded by some positive number, but it wouldn't necessarily have to settle down to be a limit. So something like sine or cosine, as x goes to infinity, you can't say a single answer for limit x goes to infinity of sine x, because sine of infinity is not a number, and it isn't infinite either, because sine and cosine, by definition, have to stay between -1 and 1, because you go back to the definition of as ratios of sides of a triangle, for example. So something like that, you see there's an m because the absolute value, say, of sine is less than or equal to 1, but there isn't a limit, single number or symbol. And so you write f is big O of g when this quotient will stay less than some positive number, but not necessarily be 0 or 2 or whatever. So we read this as f is big O of g. Little o then, f grows more slowly than g, and big O, f grows no faster than g. So if the relationship is little o, then there is a limit, which will be 0, whereas if the relationship is big O, you do not necessarily have a limit. You may have, but you don't necessarily. You just know that the quotient remains bounded. So, for example, x plus sine x is big O of x, because if you set up your quotient and divide the x into that one, so it's also the same as this, you know that sine x over x will stay less than 1 in size, because the sine is, and then as x becomes larger and larger, whatever this is being divided by ever larger quotient. So you can certainly say that the original here is less than or equal to 2, because the most that sine x over x can be is 1, and the most that this can be is 1. So you're not saying that you have a limit, but you're saying that the quotient's bounded. And if you have a thing like this, e to the x plus x squared is big O of e to the x. Again, if you set up your quotient, if you actually do your limit, you see you're going to have 1 plus limit of x squared over e to the x, which is 0. So this one actually approaches a limit, which is 1, but which is to say that this is also little o. If something is little o, if the left-hand side is little o of the function on the right-hand side, it's also big O, because if it does approach a limit, then you can also say the quotient is bounded. But you can't go the other way around. So this is also little o of e to the x, and also always, if f is little o of g, then it's also big O, but you can't turn it the other way. So I gave you the copy from the book so that you would see how the print looks, and then I have the what is in my handwriting, which is essentially what's here.
Yeah, it does.
This is for that. Well, I'm just gonna do it now. All right, if you're determined to.
Store the functions.
Oh, yeah.
And,
So you store the function, then execute another.
You can, but I don't think you need to do
Oh.
a series.
You mean in Maple?
In Maple, yeah.
Yeah.
Come back to our application of the big O idea. If you look at what is the remainder theorem for Taylor's series in powers of x minus a, then you focus on a particular x value, say x equals b, say that you want to compute your function by using a Taylor series at some value x equal b. So f of b is, and what you're using is the number a to evaluate your function and all the derivatives. So the a, if you were thinking of getting the Taylor series for sine or cosine, requires a value where you know exact values, if possible, so that you don't have any round-off error. So, for example, the one that we will work with over there under the clock is sine of 31 degrees. So your A would be 30 degrees because sine and cosine have exact values at 30 degrees, pi over 6. Then in radians, being 30 degrees, the sine is 1/2 and the cosines are at 3 over 2, which are exact. So typically, the A is something like pi over 6 if you were thinking of sine of an angle that's near 30 degrees. The B would be the actual angle for which you want a decimal to put in your table if you're back in the 1700s building the tables for the trig functions by hand. And that's then the math books all had tables in the back of the book until the 1970s and the development of the student scientific calculators. These calculators that you can buy for something like $10 now that'll do the trig tables and log and so on, came out, the first ones were out in the 1970s, and they were very expensive. I think that the first ones that we had at Boise State were made by Hewlett-Packard, and they were just a student scientific calculator. They weren't graphing calculators. And I was the math department chair at the time, so we bought 2 of them for the math department. These HP, I think the model number was 45, and they were $500. And the tuition at Boise State at that time was about $100. So $500, you could almost go to college there for the semester. I mean, as far as books and tuition, you could. So it was a lot of money. Well, this, of course, is Moore's law and the price of computing power and how much you get, and it's certainly been true. But the point is that people used these tables originally done by this sort of thing by hand for literally hundreds of years. And certainly when I went to school, that's what it was. And the table was in the back of the book and so on. Well, anyhow, the nth Taylor polynomial would be something like this, which will have a degree n, and then the remainder will have degree on the derivative n plus 1. You evaluate this next derivative at some point in between a and b, and unfortunately, you never know exactly where. If you could do that, then you could get an exact value here, and you'd be essentially getting something for nothing. You'd be getting what is an infinite series with just a finite number of terms. So the best you ever can do with this is to try and say, well, the magnitude of the derivative cannot be larger than something, and get a ballpark on your error. And then you have x minus a, n plus first power. This number is going to be, in Maple, it's going to be like 6 if it were a thing where you're using this polynomial and then O of x6, for instance. And then whatever this number is and the order derivative, that number factorial is in the bottom. This is the form of the remainder and essentially the error term for Taylor series due to the French mathematician Lagrange, and I didn't write his name. Let's see where. Okay. And this is, I think, the most useful form of the remainder theorem. So the place where the value of the n plus first derivative would be taken for this to be exact could either be between a, where you're evaluating your derivatives, and the b, where you have the value that you want to put in your table, if the b is larger, or it could be the other way around if the b is smaller. In other words, if you were talking sine of 31 degrees and working with powers of x minus pi over 6, which would be like 30 degrees, then the c would be between 30 and 31 degrees. But if you were using the series to do sine of 29 degrees, the 29 degrees is less than the a, which is 30 degrees, and then you'd have it the other way around. The b is less than the c is less than a. So we don't know an exact value for c, but we can work to find an m where the maximum magnitude of the n plus first derivative will be less than or equal to m over the interval between where you're evaluating the sine, let's say 30 degrees, and where you're trying to get a number to put in your table, which might be 31 degrees or 32 or 29 or 28 or, of course, somewhere between. Well, for sine and cosine, things are especially nice because they're never bigger than 1 in size, and your derivative is never anything else except sine or cosine. So you can use capital M equal 1, and That's what we're going to do over there under the clock. Meanwhile, with the example with which we started, where we were talking about series for this, and if you wrote 6 in the maple command, what you got was a polynomial of degree 5, which includes 6 terms, count them, and then the symbol O of x6. So then that goes back to the handout with the maple, and there's probably some people who got here and didn't get this.
No, I think there's some.
You got this one? You got that? Did you get this one? The maple. If you notice what I did there, this goes back partly to what we were doing last week with the logarithm. First I got the series for 1 over 1 plus x. Then I'm defining the corresponding Taylor polynomial as g. And then I'm integrating g. So term by term, that's line 4. And so line 5 then, you get the x minus a half x squared. So that's the series for the integral of 1 over 1 plus x, which of course is log of 1 plus x. So line 5 is the series for, well, it's the first 6 terms of the series for log of 1 plus x. And then I did the same thing over again with the series for 1 over 1 minus x and integrated. And so line 11 is the first 6 terms of the log of 1 over, the log of 1 minus x. And then I am adding, so log of 1 plus x plus minus log of 1 minus x. The difference of the logs is the log of the quotient. I'm down to line 13. So I have finally, if I add the series, line 14, the series for log of 1 plus x over 1 minus x. See, it has the odd powers of x. And we talked about this last week. I had a handwritten handout that was doing that. So then if you turn the page, you can see, if you're thinking about something like using log of 1 plus x over 1 minus x at x equal a third to compute log 2, you can see the fit between the Taylor polynomial and the actual log of 1 plus x over 1 minus x. And you see that between 0 and about a half anyway, your eye can't tell the difference in the two graphs. So you have a way to get at logarithms generally, and log 2 particularly if x is a third, that is reasonably efficient. And then I have the Taylor polynomials for various values, and you can compare the decimals with what your calculator would say for log 2. So then if you go on to the back side of the second sheet of paper, you see that I'm doing the same kind of thing for the side, which I've been talking about going on with. So that brings us into getting the Taylor series appropriate for sine of 31 degrees. So 31 degrees is 31 pi over 180 degrees. Remember, you have to use radians because in calculus, it's always radians for trig functions because the derivative of the sine is not the cosine unless you're in radians. If it's in degrees, you've got pi, you've got a chain rule problem, you see. And so you've got pi over 180 degrees times cosine, every time you open your mouth. So that, in a sense, that's what radians were invented to do, is to make simpler formulas. So anyway, it's 31 pi over 180, and that's 30 pi plus pi, and 30 pi over 180 is pi over 6. So what you want to do is evaluate sine and cosine at pi over 6 because you have exact values. So that's going to be the A, and then the B would be, if you want 31 degrees, the B minus A would then be pi over 180, which you notice is on the order of 1 over 60. It's a comparatively small number. To get fast convergence, meaning that you don't need very many terms of a Taylor polynomial, you want to have it so that the difference between the table value you're trying to compute and the exact value you have for the derivatives is as small a number as possible. So for example, with the log 2 computation, we used powers of x, in other words, powers of x minus 0. And then for log 2, if you're using 1 plus x over 1 minus x, your x is 1/3. So your value, the equivalent of b minus a in that computation is 1/3. Well, this one is more favorable. This is more like 1 over 60. And you see, the smaller that number is, the fewer terms you're going to need for a given level of precision, 5-place table, say, or something like that. When people were first doing the tables, they thought that a 4-place table was plenty good. And later on, people went to 5-place tables and so on. But anyway, what we would have then is sine of b, whatever it is, such as 31 degrees, is sine of a, whatever that is, such as 30 degrees, plus the derivative of sine at a, then b minus a over 1 factorial, and so on. So if you look at the sine, your pattern of derivatives is sine, cosine, minus cosine, then you repeat yourself. The derivative of this is back here, and so on. So this is the 0-order derivative, which is the function, then add 4, then next would be another 4, 8th derivative, and so on. So you only have 4 possibilities. And so your values are a half, or 3 over 2, or those numbers with minuses. Your coefficients can't be anything else, as I'm saying here. So your sine of 31 degrees, then, you see you have your f of a, or sine of 30 degrees, exact value. Then your derivative, cosine, exact value, x minus pi over 6, over 1 factorial, and so on and on, like that. And if you notice, with the red and green arrows, the coefficients are either a half, plus or minus, or root 3 over 2, plus or minus. And so the way to get this in summation form is to separate the reds from the greens, because with the reds, you always have this common factor of a half and then a sign alternator. And you always have an x minus pi over 6 to some power, where the exponent will match the denominator number of the factorial. And these, where they're the red, you see this is the 0th derivative, first, second derivative, third, fourth derivative, fifth, sixth derivative. So they're the even order derivatives. If you're thinking of 0, 2, 4, 6, like that. So you're going to have the even exponent on x minus pi over 6, and then that matches the number here with the factorial. And you see this, if you start with 0, first you go plus and then minus and so on. And to get this even, n goes 0, 1, 2, but 2n is always even. And then in the same way with the greens and the cosines, you always have the root 3 over 2, the sign alternator again, starting plus the first one, and then minus, and then plus, and then minus. And you always have an odd exponent, you see 1, 3, and the denominator matches. So as n goes 0, 1, 2, 3, 2n is even and 2n plus 1 is odd. So this gets the reds and that gets the greens, and then if you want to combine that, you can have your sign alternator and then the half, and with the x minus pi over 6 part, and the root 3 over 2 with the x minus pi over 6 part. So you can finally write it as a single series with summation notation. If you go through something like this, it's more tricky to write these series than it is to just write out what the pattern is. The people originally doing the computing only would need a pattern like this because they were going to use some Taylor polynomial, such as maybe going through the cube or the square, and call it plenty good enough. And if you look at the maple now, you can see that. Now I guess that's where it is over here. So if you go back to the maple and say the line 32, which is on the start of what would be page 4, the back of the second sheet of paper there. So F is sine, and then I get maple to produce the series. You see, so 8 terms, so it goes through x minus pi over 6 to the 7. And then, as we said already, the big O means that essentially what big O is saying is that the error is less than or equal to some maximum value that your derivative could have, in the case of sine, between 30 and 31 degrees, and that derivative can't be more than 1 because it's either a sine or a cosine, and a sine and cosine are never more than 1. So that would be a 1 if you were talking about sine, and then it would be the x, which would be the 31 would be 1 degree in radians, so it would be pi over 180 here, and it would be this number, whatever I had 8 for the sine example, so it would be this number to the 8th power over so the m here would be the maximum the derivative could have over then 8 factorial. See, the maximum back here with the logarithm would be the order derivative over that number factorial. So coming here, what we would have, well, I guess what I want is the maple. Okay, here it is. All right, so you look at down there at line 34, where I'm defining the function g as my Taylor polynomial that goes through degree 7, my 8-term Taylor polynomial. That unapply convert business is just a way to get Maple to define a function g, which will be the function that we've been working with. And you could just as well type g colon equal x arrow and then type in the function that you want. Does the same thing. So then my point is that you can plot the approximate polynomial that I'm calling f, and you can plot the actual sign, which, well, the sign is f and the polynomial is g. So if you look at the next page, you can't see the difference between about minus pi over 2 and pi over 2. You notice that there are really 2 curves there, but you can't tell which one's which because the polynomial is extremely accurate. So then, if you want to get some values, line 35, value the polynomial at 31 pi over 180. You see, Maple has put in the fractions, and then you simplify that, and you see the numbers there. So if you turn the page, anyway, what you can see, if you look at line 39, where I have h equals unapply, that's a polynomial now of degree 3. So 4 terms of the Taylor series, line 39. So if you plot that and the sign, you see that then you can begin to see a difference in the graphs. If you get below minus a half about and above 1 or something like that. And still the polynomial then of degree 3 is quite a good approximation. And then I have defined the function, and the next one is the quadratic, line 40. And if you compare line 40, that graph with the graph of the sine, you see you're still quite good between 0 and 1. So where the 0 is, where the origin is, that's an A. So because you're working with the differences from 30 degrees. So if you look at that picture going 0 to 1, that's really the interval between 30 degrees and 31 degrees, because 31 degrees is the 1 unit away from the 30. And so even there, your maximum error is very small. Now, better do this before I. You to do in these problems in 10.9 is use some of the series for which we know the form, like the Maclaurin series for sine and cosine in each of the x, and so on. And then by substitution or by adding series together, that kind of thing, which you can do in the intersection of the intervals of convergence. They want you to produce series for other functions without doing all the derivatives. So for example, you know that the Maclaurin series for sine is, if you use a letter U, looks like this, and this is actually the interval of convergence is all values. It's minus infinity to infinity. You could prove that using the ratio test, for example. And so then if you look at problem 4, from this you can get the series for sine of pi over 2 times x, because you simply replace the u with pi over 2x, and then you notice what this is. There's a sine alternator, and the exponent is odd, so sine alternator, exponent on u then is on pi over 2x, the odd number, 2n plus 1, and the denominator number matches the exponent with a factorial. So it would start out like this. If you look at number 14, it wants the series for this function, sine of x minus these two terms. So f of x is sine x minus x plus x cubed over 3 factorial. So write your first terms of your sine series, and then subtract here. So minus x, 2 minus a plus x cubed over 3 factorial. And then you notice those cancel and those cancel. So you get this series. You get all of the sine series except the first two terms. Okay, number 24 wants the series for f of x where it's the product, sine cosine. So there are two ways you could go after this. One is to do what we call the quotient product, which is tomorrow's class, part of tomorrow's class, where you'd actually take the first few terms of the sine series and the first few terms of the cosine series and start multiplying them like you'd multiply polynomials. And what you'll get is the first few terms of the series that they want. The other way you can do it in this example is trig identity. 2 sine cosine is sine of 2x. So go back to here and use 2x for u, and then what you want is a half of the sine 2x series, which is what the book does. So you have the half because 2 sine cosine equals sine 2x. You have then 2x for u there and so on. And that's like what I did here. I'm taking 2x and raising it to an odd exponent and dividing by n plus 1 factorial. And then you can do you can play some games. You can take the half across the summation symbol. You can take a number across the capital sigma the same as you can take a number across an integral sign. Because the integral, after all, is a limit of a sum. And so the rules for what you can take across the integral sign match the rules for what you can take across the summation sign. So you can take this half inside, and then where you have a product all raised to the power, you can take each factor raised to that power. Because you have matching powers, so you can take the 2 times the x, and this is the common power, and that gets you back to there. And then if you take this, if you think of 1/2 as 2 to the minus 1 power, when you multiply, you add exponents, so 2 to the minus 1 times this, you have 2n plus 1 minus 1, so you have 2n. So it leaves you 2 to the 2n, the x to the 2n plus 1 over n plus 1 factorial. So that's kind of clever, but that's what they want. So problem 25 wants you to add series term by term. So if you have the intersection of 2 intervals where one series converges in interval I1 and the other one in I2, you can add the 2 series and say that series converges in the intersection. So for example, e to the x, the interval is all x. And 1 over 1 plus x, the interval is the open interval, minus 1 to 1. So inside, so the intersection of this with that is minus 1 to 1. So inside that, you can take the e to the x series and the 1 over 1 plus x series and add. So 1 and 1 are 2. Those are gone. Then you have x squared over 2 factorial plus x squared. This is a 2 and this is a 1 in the denominator. So you get 3/2 x squared. And then this one, this is a 6 and that's a minus 1. So you get minus 5/6. And then this is a 24 and a 1, so you get 25/24. So you actually have a pattern for this that you pick up over here. So the one, the e to the x series, you always have 1 over n factorial, and the 1 over 1 plus x series, your coefficient is either plus 1 or minus 1, because it's 1 minus x plus x squared minus x cubed, and so on. So if you recognize that, this is your formula for your coefficient. And you see, then you either have 1 over n factorial plus 1 or 1 over n factorial minus 1 as your coefficient. Okay, and then 26 wants cosine minus sine. And each of these is valid for all x. So your difference formula is valid for all x. So this is your cosine Maclaurin series. If you haven't noticed, there's a page in your book toward the end of chapter 10 that has Maclaurin series for common functions like that, all on one page. It's maybe in the section 10.10 or 10.11. It's in there toward the end of the chapter, you can find it. And anyway, here is your sine series, and you're going to subtract. So you notice I have a minus sign out in front. So if I bring this in, then I have minus plus minus plus. And then you notice these are even exponents and these are odd. So when I combine these are gonna go in between the even terms. So you're gonna get a thing that's like this. And the book leaves it at this point. You notice that you have a pattern. After you get started, you have 2 minuses, 2 pluses, 2 minuses, 2 pluses, and so on. Okay, so one last comment then on the remainder formula. You see what we're saying with the big O, if you were back to the example where we started, where you had the function 1 over 1 plus x, your actual remainder formula from Lagrange form, it would be the 6th derivative over 6 factorial x minus 0 to the 6th, because you're evaluating these derivatives at x equals 0 if you write it as a power series. Okay, so then what's O of x6 is really the Lagrange formula, meaning that over x minus 0 to the 6th, which is the 6th derivative over 6 factorial, is some maximum number, some bound. The m then would be the most that the 6th derivative could be in the interval where you're working, divided by 6 factorial. And so that, even though you don't know exactly what value this is, to get this as a specific number, you can use something that would be the most this could be over 6 factorial. So then that says that the magnitude of your error is less than or equal to whatever is this maximum that this quotient could take times x minus a to the 6th. And so if you're working here with a number that's comparatively small, like pi over 180 for sine of 31 degrees, what you have is an m, which is the most the derivative could be, which is 1 for sine or cosine. You'd have the 6 factorial in the denominator and a number like pi over 180 to the 6th power, which is a small number. It's like 1/60th, 6th power, if this were the pi over 180. And then you're dividing that by 6 factorial, say, something of that kind. So that's why these polynomials usually don't have to be very high in power to get good values. 4 places, 5 places, anyway. Okay, so the last day to turn in homework, for those of you who do written homework or want to do written homework to make up missing my math lab, would be week from today, 28th, or week from tomorrow if you come to class, which you may or may not do. So tomorrow we'll do binomial series, the last section in the chapter, Cauchy product limits. A week from today we'll talk about computing pi, and then a week from tomorrow you can come take the final if you want to take it early, be done with it. If you don't want to, don't show up, and you can come on May 5th, which is 2 weeks from today. And you have the big sheet of paper that says what the questions are about. However, they're not necessarily in that order. Okay. So any questions about what we're doing the rest of the semester? Well, come back tomorrow and hear about binomial series and terms, the first one. And so then there has to be an interval of convergence to talk about. And it's limited, and it's not all x, like sine and cosine and e to the x. And it actually depends on what the n is exactly. Regardless of the n, these binomial series all converge when the absolute value of x is less than 1. So minus 1 to 1 is your basic open interval, to use the language of test 4. 1, so you get minus a half, minus 3 halves. And then for f triple prime, reasoning in this same way, you get minus a half, minus 3 halves, minus 5 halves. And for f fourth, you'd get, you notice your numbers here are 1, 3, 5, and then you have a power of 2. And then this would be 1, 3, 5, 7, and the next power of 2. So that's your pattern. So your binomial series, which is the Maclaurin series, really, for this, for 1 plus x to the minus half, is f of 0 over 0 factorial, f prime is 0 over 1 factorial x. Remember, when you're building a Maclaurin series, you get these coefficients out of your derivatives, and part of the series then is first term times x to the 0, next term times x to the 1, next term times x square, and the part of the series also is the first, the function at 0 over 0 factorial, the derivative at 0 over 1 factorial, second derivative at 0 over 2 factorial. So what I'm getting for the f of 0, f prime of 0, f double prime of 0 comes out of this. And then the 0 factorial, 1 factorial, 2 factorial, and multiplying by x to the 0, x to the 1, x squared is the Maclaurin series game, the same as it is for any function that's differentiable. So when you put this together, your f of 0 is 1, your f prime then is minus a half, your f double prime is minus a half times minus 3 halves, which is 3/4. The next one, the 3 times 5 and 2 cubed is 15 over 8, and odd number of minus signs, so it's minus, and then 3 factorial x cubed. Then this next one would be 105 over 16 over 4 factorial x fourth. So this is a binomial series, as it's called, but it's really a Maclaurin series for 1 over 1 plus square root of x. Well, why is that so important? Well, turns out it's very much so if you're thinking about physics. Because if you're in the physics class and your object is moving with speed v, and if c is the speed of light, 3 times 10 to the 10th centimeters per second, say, and that's, of course, a great deal faster than things that we make. And so it's correct to have a whole bunch of inequalities there. Then your v square over c square expression would be very much less than 1. And remember that you have convergence for a binomial series, regardless of what the n is, in the interval between -1 and 1. So we don't have to worry about endpoints. unless you get something up at the speed of light. And that's faster than cars go, although sometimes you wonder if you're trying to walk across the street, they're after you. Anyway, replace the x here by v squared over c squared. You might wonder why this particular choice, but be patient. And so then what you have is, well, I should have said with minus this. So then your 1 over 1 plus x is 1 over 1 minus v squared over c squared, square rooted. So I'm just going back to here and replacing the x with minus v squared over c squared. And then here you have it squared. And then here you have it cubed. So you get this series in terms of v squared over c squared. Well, in physics, total energy is kinetic plus potential energy. And Einstein tells us, or he did about 100 years ago actually, that an object moving with velocity v has total energy, its mass that it has when it's going at speed v, times c squared. Again, c is the speed of light. And an earlier physicist, Lorentz, gave us the relationship between the mass when it's moving speed v and what he called the rest mass, which is what something would measure as its mass if it's not moving. And what is called the Lorentz transformation, which is something Einstein had to work with, where m0 is the rest mass, is this relationship. So that's why I'm talking in my series about v squared over c squared. So then the total energy is the mass, which then I'm replacing with this formula, times c squared. And then what I can do is take the 1 over square root, 1 minus v squared over c squared, and write the series for it. This is a standard sort of derivation that you see in a physics or physical chemistry class or engineering classes, where you're working with some function and then you take the function and expand it in its Maclaurin series or Taylor series, as I'm doing here, and then you keep the first 2 or 3 terms of the series. And that's an approximation, but it's usually a very good approximation. You see people do this in scientific work all the time. So that's that's a lot of what this chapter is for, you see, as well as seeing how people originally made the trig tables and the log tables and so on. So I'm taking my 1 over the square root and replacing it by this series. And you notice that while the original series that you get using the letter x is an alternating series, if your x happens to be minus v squared over c squared, as you put that in the term here where you have the minus sign, you have minus times minus, which is plus. Then in the next term, where you have a plus sign, the x is square, so then this is square, so this is positive. Then again, you have an odd power. You have this minus and the minus from your cube of minus v squared over c squared. So this series in terms of v squared over c squared is all positive. Okay, so your total energy then is, if you multiply through, you see you have m0c squared, which is what Einstein then called the potential energy that's there simply because it is an object with mass m0. So that's the basis, say, theoretically, for atomic energy. And we have since proved that it actually works. And then if you notice what happens next, if you multiply on through by m0c squared, this term, you see that the c squared cancels that one, and you have a half what would be m0 v squared. And that's what Newton called kinetic energy when he originally developed physics for us. And this would be the object with its mass as its rest mass. And then you see there are these higher order terms. The third term, this c squared would cancel into the c fourth, and you'd have v fourth over c squared. Well, generally, this is essentially zero, and so are the rest of them, because the speed of light is so much more than what people ordinarily can make things go. But it is there, in the theory at least. So in a sense, Newton's kinetic energy is actually an approximation that certainly is good for most things that we do and so on, but then there are these other terms. So this is an example, you see, of what we would do with what we call a binomial series, where we can expand an expression in a binomial series and then do a physics department type derivation with it. Well, this is the main thing that binomial series are used for, is something like this. So let's see, I have binomial series notes. That, well, today we've started talking about the binomial series, and we're about to go on with Cauchy products and limits using series. Thursday of, let's see, Thursday of next week, I'll talk about computing pi, and there's more to it than you might think. And I'll also talk about what's called the Euler formula, which is how you can write values of complex numbers using sine and cosine. And then Friday, a week from today, you have your choice. You can come to class and take the final, or if you don't want to take it until time in finals week, then don't come to class next Friday and come on the following Thursday, May 5th. And unless I have a car accident or some other disaster, I'll be here a week from today, and also the following Thursday at 7 if you want to start early, and you can work until what would be the normal end of class time, which is whatever it is, 10:30 or something like that. And so you have the big sheet of paper which tells what each of the questions is about, and I give you a reference number by what section to look in the book for the formula that you'd need and so on. So what I encourage you to do is to go through this and look in the sections and either write down the key formula or write down the page number so that you can find it quickly. Because if you figure, well, I'll read the book during the final, you'll run out of time. And that's more than enough time. That's all the time I'll give you, in other words. So if you run out of time, well, that's just too bad. You ran out of time. Okay, so of the 19 questions, the first 6 of them, I think it is, are multiple choice, and then the rest of them are, there's a space on a cover sheet where you're supposed to put a short answer, and then there's also space in the booklet where you can show some work. That's aimed at making it possible to give partial credit for those, but the 6 that are multiple choice, you don't get part credit. It's right or it isn't. Okay. So you can do whichever you want. You can come a week from today, or you can wait until the Thursday, which would be the time in the finals week. Okay, so I guess formalities might there be. Who knows? But I'll try. Okay. So let's start talking about kosher product, as it's called. If you remember the section in Chapter 8 on partial fractions and the method for getting the coefficients for partial fractions that I called poles and residues, that goes back to this French mathematician named Cauchy. And so Cauchy actually did a lot of important things in mathematics. So, for instance, in the problems in 10.9, 29 through 34, they want the Cauchy products for the series that would be e to the x times sine x. And the alternative would be, of course, that you could say that's your function and write the Maclaurin series, get f of 0 and then f prime of 0 using the product rule and go like that. But if you notice, there is a page in the end, I think it is, of section 10.9, or else it's section 10.10 in your book, that has a box with commonly used Maclaurin series in the box. And so you can find the series for sine x and the series for e to the x. So if you look, your sine x series starts x minus x cubed over 3 factorial plus x fifth over 5 factorial. And your e to the x goes 1 plus x squared over 2 factorial, so on like that. So what you do is start out multiplying these as you would multiply polynomials. Notice that these are polynomial type expressions with more than 2 terms, so you can't really just use the FOIL method that they have taught in high school and so on in this country now for quite a while. What you do is multiply the way that people did multiply even 2-term polynomials before the people in math education started having everybody use the FOIL method, which is probably how you've learned it. And this is what you call vertical format. And so it wouldn't matter, in theory, which function you put on your top row and which is the bottom row. So whichever way you do it, then you start at the left on your bottom row, and you multiply that entry by everything in the top row. And of course, these are actually infinite series, but what you're doing is you're taking just the first few terms to get a pattern. And the book in the problem wants the first 4 non-zero terms. So what you have to do is take enough terms to be sure that you have all the possibilities that correspond to a given power of x. So I take the 1 times x, you see, follow the green arrows, and that gets me x minus x cubed over. Now, instead of saying factorial, I put the value, the 6. The other thing you have to do, you notice this is odd, 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 but when you multiply by x down here times this x, you'll get an even exponent. So when you arrange your work, you want to leave enough space between columns that are odd exponent to put in columns that are even exponent. In other words, your first row of products, 1 times these, does not allow for all of the exponents you might eventually have, because it skips over 2 and skips over 4, skips 6, and so on. So you gotta leave some space. And then take the next term here, the x times that, and as I've been saying, that's even exponent, so that goes in here, and then you'd have x times x cubed, so that'll be an x fourth, and then the 3 factorial is the 6, and then this will be x6, and 5 factorial is 120. And then this one, you'll have an x squared times x, so you see you have another entry that's x cubed. So this one is going to be an x cubed over 2. And like you do in algebra, then you're going to add like terms, where like terms means like power of x. It's the same stuff that you always have to keep straight in an algebra class. And so I'm using the blue color now, then this one will be x fifth. This is a 2, and that's a 6, so over 12. And then the next one would be an x7, and 5 factorial is 120 times 2 is 240. So what they wanted was the first 4 non-zero terms, so probably you wouldn't need to get any further over than the x6 row anyway, and perhaps not that far. So then, looking at the kind of pinkish color, we have an x fourth over 6, and that goes in the x fourth column, and then you'd have an x6 over 36, and that would go in this column. And then if you go another one, 4 factorial is 24, you have x4 times x is an x fifth increase. And so that's the x fifth over 24. And so let's add like terms here, which is x, here, which is x squared, here, so you have a half minus a sixth, which is a third. And then you notice these two happen to cancel out. And it says the first 4 non-zero terms, so we have to go one more. So we have to look at the x-fifth column and add the 1 over 120. The 12th is 10 over 120, and 5 24s are 120. So you're adding these fractions, which would be minus 4 over 120, which reduces. And so those would be your first 4 non-zero terms. So you have to be sure that you take enough possibilities if you're going to go through x-fifth, as in this case, that there's no other way to get a product when you add exponents to be an x-fifth. You have to be sure you're not missing anything that would be x-fifth. So you can do Cauchy product like this, and you can also do quotients in somewhat the same way. I have a quotient down on that end, and we'll see that in a minute. Meanwhile, take a look at problem 30, which wants the series for log of 1 plus x over 1 minus x. Well, in this one, what you do when you have a denominator like this is you try to rethink the problem so that it's a product. And you might have to do long division to get the series for 1 over 1 minus x. Actually, it's a series that we have done. It's the geometric series where 1 over 1 minus x is the sum of it. So it's a geometric series where the common ratio is x. So if you recognize that the geometric series that this is the sum of is here, 1 plus x and so on, then that's the series for 1 over 1 minus x, and you can just write it down and work it as a product, as I've done here. If you did not recognize from the work we've been doing that the 1 over 1 minus x corresponds to this series, you could actually do long division, start in dividing 1 minus x into 1. I've done a long division type on the far end, which we'll do in a minute, so wait for that. So assuming I know this series, it's also one that's given in the book, then I have the log of 1 plus x series, which we also have done in working with the logarithm. So assuming that we have these series, then we can start the Cauchy product again. So you see you have 1 times x, 1 times minus x squared over 2, and so on, with the green up here that I've written in green color. So then I move over, and I have x times x, which is that color. Then I have minus x cubed over 2. I have plus x fourth over 3, minus x fourth over, the x here times the x fourth over 4 gives me the minus x fifth over 4, and then the x times that would give me x sixth over 5. Again, he's asking for the first 4 non-zero terms, so this is way more than I needed to do. Take the x squared times x, you see, and you get another x cubed. And then times this one, you get a minus x fourth over 2, and then an x fifth over 3, and an x fourth rather over 3, and let's see, it's this one, and then minus x fifth over 4, and so on. So then finally, if you do x fourth times, let's see, if you do this one, the x cubed times x, you get the x fourth. You do the x cubed times minus x squared over 2, that gets you the x fifth. So we have an x, we have x squared minus x squared over 2, so we have x squared over 2. We have 1 plus a third minus a half, which is 5/6 x cubed. And then we have 4 of these, you see, that are x fourth. So we have 1 minus a half plus a third minus a fourth, which ends up being 7/12. Some of you have calculators that'll do fractions, which is handy if you're doing stuff like this. Sometimes fractions can get kind of nasty if you have to do them by hand, certainly. But this is the idea. What you're actually getting is a series for a quotient, but you're managing to scheme out of the quotient to an extent by making it into a product sort of thing. And you can always do that because whatever your quotient is, you can think of it as 1 over the denominator times the original numerator, and then if you get the 1 over series, which may require long division, then you can finish it as a product. So let's, while we're on the subject of Cauchy product things, let's look at the one that I squeezed in over here. So what I'm after finally is the series for the tangent. And I'm thinking of tangent as sine over cosine. So what I want to do is get the series for secant, which is 1 over cosine. And then if I have the secant series, thinking of it as 1 over cosine, I can do the Cauchy product of the sine series with the 1 over cosine or secant series. And that gets me the tangent series. The alternative to that, of course, is say your function is tan x and then do the derivatives. The catch on that is the derivatives become nasty, you see, because the derivative of the tangent is the secant square, and then the derivative of that is chain rule. It's 2 secant times the derivative of the secant, which is secant tangent, and it just it balloons on you see. So it's kind of like credit card debt, something like that, you see, that just balloons until it drowns everybody. So anyway, start out with the Maclaurin series for secant, or 1 over cosine. So here's your cosine series, and I'm doing long division into 1. So what you put here times what's there goes underneath whatever is in here and has to match, so that when you subtract, your first column is gone. That's how you do long division, right? So I have 1 here because 1 times 1 is this one, and this line minus that one, that's gone. Then this is times everything else, as far as many terms as you wanted to carry here. So say you went another term, it would be all of that. Okay, so when you take the rose-colored line from 1 and all the zeros, what it amounts to is you change these signs. So this is now plus, and this is now minus, and this is now plus. And that would go as far as you want to go with it. Okay, so now what goes here in blue times 1 goes under whatever was the leading term here and is exactly the same. so that when you subtract black minus blue, that's gone. And so then you have the x squared over 2 times x squared over 2, so you get the minus x fourth over 4. And then you get the plus x sixth over 48. And then if you went another term here and did the product, you'd get, well, I didn't do that, but you could go on. All right, so then when you subtract black minus blue, the first column is always gone. So then you have this, you have minus x fourth over 24, and you're changing the sign, so plus x fourth over 4. And so that's 6x fourth over 24 minus one of them, so it leaves you 5x4 over 24. And then this next one will finally be, if you wrote this one with the common denominator of 720, you would have 15x6 over 720, and so you'd have one of them minus 15, so you'd have minus 14x6 over 720. So your secant, or 1 over cosine series, then looks like this: 1 plus the x squared over 2 plus the 5x fourth over 24 plus the 14x6 over 720, and I reduced the fraction, you see, by 2. And so now I'm going to multiply this by the sine. Remember, this is 1 over cosine, so 1 over cosine times sine is tangent. So this then, like the other end of the room, I'm setting this up as the Cauchy product. Here's your sine, and here's your secant series, first few terms. And I go through the same sort of thing, and I get x, and then a half minus a sixth is a third, x cubed. And then I have, with these, if I get to the 120 as the common denominator, and I did it right, if I did it right, I get 2x fifth over 15, and so on. And you notice that I gave up with this one. The fractions, you see, you have minus 1 over 5,040, and then you have 1 over 240, and then you have minus 1 over 144, and you have plus 7 over 360. If anybody has a calculator that does fractions and you want to tell us what the exact fraction is out of these, why, that's fine, but it's beyond what I could do in my head. I am deteriorating. Okay. So anyway, regardless of whether I get this next term, this is how you do something like tangent. You see, do your 1 over cosine and then multiply by sine. And if you were doing this by hand, it's really better than trying to do the derivatives of the tangent, because they get so messy. Well, meanwhile, let's come back over here. Another type of thing you do with series is you can use series if it's a definite integral and it's something for which you cannot get an antiderivative in closed form. You remember all the tricks of chapter 8, where we could integrate by parts, U substitution, partial fractions, trig substitution, all those various games. No matter how adept you are, there are a lot of problems where you cannot get a closed form antiderivative. In other words, you can't work the integral in the sense of what you think of when you're in chapter 8, working to another function that you know that you have the derivative of. And one of them you cannot do is sine of x squared. You see, if you had an x here with the dx, then you could. Then you'd say that's u, and x dx would be du over 2, and so on. But without the factor of x, you can't do this in the chapter 8 sense of working the thing. However, as a definite integral, you could do it with something like Simpson's rule, of course, but an alternative to Simpson's rule, which we studied in chapter 8, remember, you could write the Maclaurin series for this function, because you know your sine series function, here it is, first few terms, so then the first term would be x squared, and the next would be x squared cubed over 3 factorial, and the next would be x squared fifth over 5 factorial. And these term by term are polynomial types, so you can integrate them. So your definite integral then is the integral of x squared minus 1 over 3 factorial, the integral of x6, plus 1 over 120, the integral of x10, and so on. So you integrate those as you know how to do, and put in your limits, and you notice in this problem, the lower limit values are always 0, so it's just 1/3, 2/10 cubed, minus 1/6, minus 1 over 6 times 7, so minus 1/42, 2/10 to the 7th power, and so on like that. So what you get here is an alternating series, so you know it converges, and your error is less than the size of the first term to drop as an alternating series. So you notice that you're going to have, if your upper limit is 2/10, you're really dealing with quite small numbers. 2 cubed is 8 over 10 cubed is 1,000, and then 3. So the first term here is 8 over 3,000. And if you just called it that, the error is less than whatever would be 2 to the 7th over 42 times 10 to the 7th power, which is 10 million. So the question says take enough terms so the error is less than 1 in 1,000. So if you dropped this term, if you just used the first term, the error is less than what this is, which you see is a whole lot less than the precision they said. So often you can get a good enough answer for a definite integral if you can't get the exact antiderivative by getting the power series for whatever the function is and doing something like this. Here's another one of the same type. Let me swallow some water here. So sine x over x. Again, you would think maybe you could integrate that by parts, but it won't work. So what is called the sine integral is this integral, and people use it enough that people have actually made tables of values the same way they have the tables, made tables for the trig functions and log. You don't find it on a regular calculator, but there certainly programs that will give you values for the sine integral. And people in times past actually have made printed tables. I don't know now exactly where you'd find one, but it's been done. So what you could do is your Maclaurin series for sine, as many terms as you think you'd need, divide by x. Well, you see then you still are integrating polynomials. So you're integrating 1, then this would be x squared over 6, and x fourth over 120, and so on. So again, you notice you're going to have an alternating series because it's based on the sine series that alternates. So you integrate these term by term and evaluate at 1/10. And again, your error is no more than the magnitude of the first term you drop. So if you did the first two terms, you'd have something that's approximately this, and then your maximum error would be 1/6 times 1/10 to the minus 7. So it would be 10 to the minus 7 over the 6 and over the 7, which is from the this term in the Maclaurin series and the 7 factorial, which is the 5040. So you're talking an error that's like 10 to the minus 12. So you see, you can get very accurate values by doing things like this. The last thing for today then, you can also use expanding something in a series to verify that L'Hopital's rule does give you the right answer. So, for example, the limit as x goes to 0 of e to the x minus 1 plus x over x squared. Let's see, I said something wrong there. It's actually the form 0 over 0, but that's an indeterminate form already. You notice e to the 0 is 1, and if you put a 0 there, that's gone. Then you have 1 minus 1, which is that 0, and over here you have 0 squared. So you could get the value with L'Hopital's rule by doing the derivatives. Let's look at that first down here. So if you do the derivative, then you'd have e to the x again. That would be gone, and then there'd be a 1 there. So you'd have e to the x minus 1 on top, and the derivative of x squared would be 2x. That's still 0 over 0. And if you go again, you have e to the x over 2, and take the limit then, and that's a half. So what I want to end with is showing you that we can get to that limit by writing the Maclaurin series for e to the x, a few terms, and take away the 1 plus x. So you see the first two terms here cancel with those two. And it leaves you x squared over 2 factorial, x cubed over 3 factorial, and so on, over x squared. Then the x squared will divide into this. In other words, you can factor x squared out of this, as I have, and then that'll cancel with the x squared. And then you can take the limit of what's left, which is 1 over 2 factorial, then x over 3 factorial, x squared over 4 factorial. So you have 1/2 plus 0 plus 0 plus 0. So, you see, L'Hopital's rule does work, at least for this problem. So, there are some problems in the 10.10 homework that are this type of thing also. So they're not that hard to do. But so anyway, that's the last set of homework. So the last day that I'll take homework is the last day that you appear next week. If you're not gonna take the test until May 5th, I expect you to come to class a week on Thursday, if you want to bring in any homework, okay? If you take the test a week from today on Friday, you can bring the homework with you on the Friday. Well, I'll see you next week then.